everybody. I'm Olof Kjellén, and I'm going to present this paper on selective blockchain transaction pruning and state derivability. This really work by Emmanuel Palm. He's our PhD student. He couldn't make it here, so you have to bear with me instead. We're from Luleå University, which is in the north of Sweden, as you can see from the ice cube, although we don't have ice cubes this time of year. So the outline here, we know that the blockchain size grows all the time, and there is storage need for this, and this is becoming a challenge, if not now, so in the future. And this is especially so in some applications, depending on how much data they store. And selective pruning is one mean to mitigate this problem. There are several of them. I'll go through some other approaches at the end, because this paper is fairly focused on this approach. So we'll start with that. And I will explain how it's done, and with some examples show how much space it can save, and then we'll have some discussions. So a couple of total change, most of you probably know this already. These are very recent numbers from yesterday. The Bitcoin blockchain ledger is about 200 gigs right now and growing steadily. Ethereum is much bigger, although it's younger. It's several years younger and still up to 7 gigs. And the question is first, is the growth going to be linear and predictable or not? What do you think? Well, it depends on the blockchain. In the Bitcoin case, it is pretty linear, because we know the max speed, the max number of transactions in the block, and we know the block interval, and each transaction uses as much space in the ledger. So it's pretty predictable, as long as they don't change parameters like the block size or block interval or something like that. So it's going to grow steadily, predictably. Ethereum is completely different, because it all depends on the applications and the smart contracts and how much data the applications choose to store. So it's more complicated. These are numbers that are reliable, that I can find on permissionless ledgers. It's much harder to find any numbers on permission, but you will see the same trend. Although in those situations, typically the nodes are fewer, which makes a difference, because you also replicate all this state to all the nodes. So the total amount of state stored has to be multiplied by the number of nodes. The hypothesis we're starting from here is that the more services we will have and the more data-hungry services, the more the state will grow. But what we're seeing already now in many applications, that fewer events will be truly critical with respect to global consensus ordering and double spending, etc. We see many IoT examples, for example, where you load in data into the ledger, and many of those measurements, it's not really critical which order they came in, or the order of the time stamping is good enough. Do you see where I'm coming? It's not a race condition where there needs to be an independent party making the consensus decision on who was before the other one. And we don't see so much double spending either in many applications. And this means that with less critical information, it is possible to prune. We also see that some new events in these new applications supersede old events. So we don't see the additive behavior as we have in Bitcoin, for example. The balance in an account is the addition of all the transactions into and out of that. So it's you have to basically, to get a safe estimate, you have to scan the whole ledger in order to find the balance. But we see more and more applications where you have identity, for example, tokens or things, and you want to keep track of where they are. The current owner, for example, you can find out the current owner of a thing, if that's what you're doing in the ledger, just by looking at the last transaction of ownership. Then you don't need the history in order to compute the correct current state. It's just a small difference, but makes a big difference to what we can do in the future regarding state. Also, as I already said, we see events on the ledger that summarize the state from earlier events. As I said, position of a thing, for example. If I say it's here, then it is here. I don't need to compute all the previous events to figure out that it's here. And that's a big difference. So it all depends on applications. So what we're doing in this project is reclaiming disk space by pruning. So the prerequisite here that we have is there must be mechanism support in the ledger to install some new pruning rules. And to experiment, we have used the permissioned ledger. We have used Hyperledger for our experiments, where they have chain codes, so we can build this. Some of our objectives is that each node should be able to prune independently. So this is not like something a general agreement, let's prune this, but anyone can go about this individually to save their own space, pretty much like you manage a cache locally. The current state must be derivable from the local chain after pruning. This gets back to my previous comment. We cannot never prune anything so that you cannot compute an accurate current state. And we have the objective that nodes should be fully able to participate in consensus decisions, even though they have pruned some of their data. So those are prerequisites and objectives. So the blockchain anatomy we were working with here is a basis that we make a difference. I'm talking more about the paper. There's lots of details and formal things in the paper which you can read. But essentially we differentiate between significant block and insignificant blocks. The significant blocks, typically the genesis block, don't prune anything there because there you have initial things. We should keep them. And also recent history we should keep, because a lot of whenever there are conflicts or consensus decisions to be taken, they're typically based on recent information. It's more seldom that you need old information, especially if that information is superseded. So we always keep a number of recent blocks where we don't prune any transaction inside. And the other blocks further down, you can see there, they are eligible for pruning. And that doesn't mean that we remove the blocks. That means that we can prune some transactions inside those blocks. Now, in the paper, we defined a number of properties for blocks that must be preserved. So this is rigorous work with formalism. And these are predicates that you can check before you do pruning and after you do pruning to ensure that you haven't messed up anything. These are the standard properties of a ledger like Hyperledger. So I don't go through them in detail here, if that's okay. It's defining what it means that a ledger is immutable, for example. We also have some state properties, S here. And here we define a properties that something is derivable. And that essentially means that you can derive state by having previous block and run the current transactions, or you can unwind a future block and get back to previous state. And these are properties that you need to maintain too. We also have a property retrievable. That's a new thing. That means that if you have pruned something, this can be downloaded from network peers, assuming that not all the peers have basically pruned everything. So in a big blockchain with several nodes, you can sort of dedicate a couple of nodes to not prune. They will keep the complete record. But others can prune and then be more lightweight and still be able to participate in consensus. This is something new. We have a property preserving hashing procedure. We have to change the hashing procedure slightly. So what we do here, if you prune transaction in a block, that would normally change the block hash, obviously, and that would make that block illegal. So we introduce this hashing procedure that accounts for pruned transactions. So as you see here at the bottom there, you can either have in GTIJ, you can either have the complete transaction information there in the ledger, and then you do the hash, that's the bottom one, or you have saved the hash of that transaction. So the model we're using in this experiment is that each transaction has a hash, and the block hash is the hash of hashes. So that means if we have saved the hash, you will get the same result as if you do the transaction hash and on the fly if you have the data there. It's pretty straightforward. And so that can actually mean that the block hash and other higher level hashes are maintained even though we have pruned some information. For this to happen, we need to define pruning predicates, and this is done by the initiator. It's a chain code, basically, that defines the rule, some local rules that they could be, for example, application dependent or operation dependent. And basically you can run it on any transaction. It'll look around itself about state and earlier transactions and return true or false, whether it's prunable or not. And this transaction will be applied to each transaction inside eligible blocks. And we will store the position of all the transactions rendering true in a set. So essentially, to summarize, this is the strategy in 3 phases. You don't really need to run it in 3 phases. They can sort of be running more at the same time. But essentially, we prepare to identify eligible blocks, and then we assemble data and state around them also to be able to efficiently run the marking where transactions T inside eligible blocks are tested with a predicate. And then at the end we sweep and remove them, but keep the hashes. The original hash is kept. So essentially transactions are insignificant, prunable, so the current state is derivable locally even without running it or having the original data. Significant should not be removed. So an example here, first one there, here we have a number of blocks. Sorry for the figure there, it was cropped a little. But you see there T23 in the middle. I should have a pointer, but I don't have. But T23 there in the middle can be pruned. It's a modulo, it's a mathematical operation here, so it's a modulo operation where C earlier got the value 3, you see in block B1. So running modulo on that doesn't make any difference, it's still 3. So that can be pruned because that transaction has no effect. If you look at T12, it can be pruned at the bottom, set B2, because it's superseded higher up by T22. B has a value. So even if we have lost the data, you can still scan locally this ledger and get an accurate state database. Pretty straightforward. I'm trying to make it simple in the presentation. It's much harder in the paper. If you want to have more challenge, read it. So the use case we've had here is a supply chain management, where we have warehouses at the top, we have distribution centers in the middle, and we have delivery points at the bottom. And there are routes or links, and essentially every delivery event here from any part to any part, you can also see that the arrows there, the routes, is also a part. That could be a truck or something, a delivery firm. They are registered with a node in Hyperledger Fabric cluster. And there are chain codes defined, smart contracts, to basically define this use case. The assets have identity. This is important, because as I explained in the beginning, when you start working with identity, which is a very hard problem in itself to establish identity, especially when the identity in your virtual logical space refers to identity in the real world, but that's not a problem in this paper. But it's a big problem to solve reliably with sensors and so on. So they have identity, and receivers at any level can claim loss damage. This is also very different from sending money, for example. I can send cryptocurrency to anybody without them being able to refuse it. It just goes to their account, like you do with ordinary money in ordinary banks. But assets, it's not necessarily that you want my old car, for example. So the receiver always has the chance to reject for some reasons, and the typical reason in this use case is that the goods have been damaged or even lost. And events that are related to history of successful delivery, when wares or items have gone all the way down to the bottom to the delivery points, then we know where it is, we know where it will deliver. It could even be so that that transaction contains the essential information so that we can safely remove the history of which route it took and so on. But of course, it's a game here. If you later actually need to reclaim the data, you need to find it other means. But there's always a trade-off. So we have run a number of simulations. Here is one example. 1,000 assets sent, whereof 120 are lost at route. So there is a probability function for each link in that previous figure. And we have a pruning predicate defined for cleaning up events in history related to finally agreed deliveries. And in those experiments, the chain size was reduced from 9.5 meg to 1.5 meg, so it's over 80%. There is some more detailed information in the paper exactly on what is reduced. You can see there that block sizes are reduced, but header sizes are not reduced much at all, and that's pretty expected. So, yeah. So, some reflections here. The case for pruning is application dependent. I will stay quite a long time with the reflections here. When we have applications where several events or transactions are superseded by events that parties agree on, sort of summing up the result or the state of things, then this is very applicable. They define the essential current state. It's important that such events could also be auto-constructed. We are using a fairly simple example here. We don't add new transactions, but you know, for example, if you take Bitcoin, you could very well add one new transaction that takes the whole history of your incoming unused transactions to your account and make one big transaction back to your own account. That would summarize your state and be in the chain, not in the state database. So you can play such tricks. We are not doing that in this paper. And you can keep some reference nodes that don't prune, so you can actually retrieve lost transactions if you need. The third bullet here is really important. Actually, you may think that this is useless because it's so application dependent. But in computer science, we have a long history of defining abstractions and APIs. So if you have the core functions of the ledger at the bottom, then you can establish a number of procedures that talk to the ledger, almost like stored procedures in a database, but these are outside of the ledger. And for example, there you can define primitives related to asset transfer, which we have done in our future work already. We know there are some specific operations that you need to do in almost all use cases that has to do with sending things from one person to another person, where that person must be able to reject the retrieval. You can easily see that this is a generic feature. And if you have defined those generic low-level commands, then you can define the generic pruning functions for those also, so that your ledger will auto-prune even for your new applications that use those primitives. So this is a big opportunity. There are other approaches also, complementary approaches to save state. Of course, they're all good in different respects. It's just that in this paper we haven't looked at the other ones. But off-chain solutions essentially means partitioning over the top, Bitcoin Lightning or other essential peer-to-peer solutions over the top, where you make one transaction out to some other solution, and there you can make multiple peer-to-peer transactions and then write back the final result. Sharding, that's essentially what was in 2 talks ago today, where you do your partitioning inside the ledger, so that some nodes have different information about different things. Sharding is, the default in databases today, traditional databases. Distributed data stores, all those that Google and Facebook and Amazon use, they all do automatic sharding, otherwise they wouldn't scale. It's not that we haven't gotten there still really with blockchains, but I think we will get there. It's just a little bit harder to get it working. But sharding is really promising as an approach. And the third one is feasible. really today. System solutions where data is stored in traditional distributed data stores that are sharded, and only the relevant hashes are put on the blockchain. This is fairly similar to what we're doing, but this is not automated. The application programmer needs to know then which data to put in a traditional store and which data that will be important for the future, so they can put it on the ledger already now. You can't put them there later, then it's too late if you want to have the ordering and timestamping. So it takes more from the application developer. But that's something that, especially if you deal with IoT data, huge amounts of data, very few of those sensor measurements would be truly relevant for some conflict resolution or something in the future. So you can go about it that way. I haven't talked about speed. I only talked about storage, but speed is another dimension of scalability to increase the number of transactions per second and to obtain scalable consensus. That's a different story. I'm not going to talk about that. So, thanks. Any questions?
Yeah, thank you very much. Are there questions?
Could you please summarize how your approach differs from the traditional Miracle tree pruning as, for instance, described in his paper? For instance, do you allow new nodes to reconstruct consensus even when the whole network is pruning?
So first of all, in our approach now, we don't store data in Merkle tree. We have a simple, there is just a flat pool of hashes of each transaction. So if you would like to add them into Merkle trees, we have to make some more work, but that should be feasible. If you add a new node to the system, they should, well, depends. If they trust another node and think that their data is accurate, then they could retrieve it from somebody that has already pruned. But if they want to be really, really sure, they should retrieve it from one of these reference nodes that haven't pruned anything and then run their own pruning. Because basically nodes are responsible for their own data in our approach. Does that respond to your question? Thanks.
Further questions? Oh, thank you very much again.
Thank you.